brief moment talking about where we get these standard reduction potentials in the first place, so how we determine these, because hopefully by now it makes sense that if I have a half reaction, right, if I just have one of these halves, there's not a completed circuit, and thus I won't really get a reaction out of just a half a cell, okay? So how do we measure the cell potential for half of a cell? Well, it's done by using what's called the Standard Hydrogen Electrode, or the SHE, okay? And that electrode is constructed in the following way. So there is a platinum electrode, so a platinum wire, very expensive, and it is put into a solution that contains 1 molar H plus, which is standard concentration, as well as 1 atmosphere of H2 gas, or standard pressure. And in that configuration, so when we're bubbling in, we're forcing in 1 atmosphere of gas to bubble in this solution, so you can see the bubbles forming there. This gives us a cell potential of 0.00 volts. So we could think of it as like threshold chemistry going on here, just enough energy for the electrons to combine with the hydrogens to make H2. Or in other words, because we're forcing H2 in there, we've created an equilibrium situation with 0 cell potential. Now, notice here that this can serve as the anode or the cathode. And so that means if I combine, so in this case here, this is my SHE. If I make the SHE the cathode and combine that with an anode, and specifically an anode that's going to have a positive cell potential as an oxidation reaction, right? Because we want it to be spontaneous. We want this to be a positive number, right? When I have the SHE minus this thing, right? So this is cathode minus anode. So I'll write that down, E cath minus E anode. Then we can see we get that 0.762 volts, which is the cell potential of the zinc half reaction, okay? And of course, if I wanted to determine the cell potential of copper as a half reaction, right, then I'd have to switch that position because the copper has a different sign than the zinc reaction as a reduction. So now I make the SHE the anode and combine it with a copper half. And what I get out of that is the standard copper reduction, the 0.342 volts, okay? And then, of course, we could remove the SHE and then recombine this zinc and copper, and we recognize that we want to make copper the cathode here and zinc the anode, and then we'll have the combination of that 0.762 volts and 0.342 volts, right? We'll have to add or subtract those to get what our cell potential would be for the zinc copper situation. But like I said, to know the individual half, right, we have to combine it with one of these types of electrodes, in this case, the standard hydrogen electrode. So as it turns out, this SHE is not very practical to use. It's difficult to arrange this H2 gas bubbling into solution. Platinum is very expensive. So we have other alternative electrodes that we can use to determine standard cell potentials. And the most common one of that is what's called the silver chloride electrode, okay? And so this is comprised of a silver chloride electrode, so a piece of silver chloride solid, right? So that's our actual electrode material. It's in a solution of saturated potassium chloride, and all that does is give us, a source of chloride, okay? And then the following reaction will occur. So it goes silver chloride solid plus electron, and then precipitates out silver, and releases chloride ions into the solution. And this is not a zero cell potential. It's actually 0.222 volts compared to the standard hydrogen electrode. So of course, first, to make this electrode, we would have had to have started with the standard hydrogen electrode as the cathode. And then we would want this silver chloride as the anode, right? So that gives us the 0.00 for the SHE minus 0.22 volts to give us the positive 0.222 volts, okay? So once that's established, now we know that this electrode is going to be 0.222 volts instead of 0, right, for the SHE. And in that case, we could still use this silver chloride electrode to determine, let's say, the cell potential of zinc in this example right here, okay? And instead of it measuring, so if it was SHE, so I'll write that down here. If it was SHE, the standard hydrogen electrode, it would have been E cell equals, so the SHE would have been at the cathode, 0.000, and the anode still would have been our zinc reaction, which would be negative 0.762 volts. And that would give us that 0.762 volts, as you can see measured right here. However, if we did this with silver chloride electrode, instead of getting 0.762 volts, we would have got 0.984 volts. All the same, we knew already that the silver chloride gave us 0.222 volts. So we would have measured 0.984 volts, and then we could back calculate that the zinc anode had to have been 0.762 volts, okay? So again, these kind of two main electrodes that we use as our reference point. You can see like that's the title of the section. Standard hydrogen electrode is kind of like the ultimate. But as it says here, it's cumbersome, it's difficult to use, it's expensive because it has platinum. So instead, these silver chloride electrodes are far more common. You just have to recognize that you've got this factor of 0.222 volts that you have to subtract out of your half, right? So that you can get the actual standard reduction potential of whatever half reaction you want, okay? Awesome.